You are listening to Quantum Photonics, and please note that you can search for us in our YouTube channel. We had uploaded some recordings of the recent speakers that we had, the recent rooms. So today we have a very interesting topic. And one intriguing hypothesis is that the universe's shape and structure might reveal themselves through the peculiarities of the cosmic microwave background, the afterglow of the Big Bang. Imagine the universe not just as a vast, endless expanse, but potentially having a more complex topology, perhaps akin to a donut or a multidimensional shape. If this is the case, the shortest distance around the universe could be surprisingly small, just larger than the horizon diameter we observe. Observationally, we haven't yet found conclusive evidence of these matched temperature circles in the cosmic microwave background that would confirm such topologies. However, the absence of these circles doesn't rule out many possible shapes that the universe might take. Our current constraints leave us with a myriad of possibilities to explore. Searching for these topology signatures within the observational data is a monumental task, and it involves analyzing extensive datasets for subtle multiple correlations that could indicate a non-trivial topology. The computational effort required for this is immense, but it's a challenge worth taking as it could fundamentally change our understanding of the universe's shape and structure. Our guest speaker, Professor Yashar Akrami, is an assistant research professor, a Ramon E. Cajal Fellow of Theoretical Physics, particularly cosmology at the Institute of Theoretical Physics, IFT UAM-CSIC in Madrid, Spain. He is also an adjunct assistant professor of physics at Case Western Reserve University in Cleveland, Ohio, and is a long-term visitor at the Imperial College London in the UK. Yashar was previously a Richard Morrison Fellow in Cosmology at CWRU, and before that, he held a junior research chair position at the International Center for Fundamental Physics, Elpen's École Normale Supérieure in Paris. And before Paris, Yashar worked at the Lawrence Institute for Theoretical Physics, Leiden University in Netherlands, the Institute for Theoretical Physics at Heidelberg University in Germany, and the Institute for Theoretical Astrophysics at the University of Oslo in Norway. Yashar received his PhD from the Oscar Klein Center for Cosmoparticle Physics, Stockholm University in Sweden, and his interests include searching for new physics beyond the standard model of cosmology, like cosmic anomalies and observational tensions, models of early universe and late-time cosmic acceleration, cosmological test of gravity, searching for the topology of the universe, implications of cosmology for fundamental theories, cosmological surveys and data analysis, the cosmic microwave background, large-scale structure, gravitational waves, statistical inference and high-performance computing in cosmology and fundamental physics, artificial intelligence in cosmology and fundamental physics. Yashar has been a member of a number of international cosmology collaborations, including Planck, Euclid, and the SKA Observatory. Yashar is one of the founders of the Compact Collaboration. So without further ado, I bring to you guys our very special guest speaker, Professor Yashar Akrami. Yashar, welcome to Quantum Photonics.
Thank you very much, Cecile. I hope you all hear me well. If not, please let me know. And I should also apologize because this is basically the first time I'm doing this on Clubhouse, my first experience. So hopefully, I'll do it correctly. Let me thank you again for the invitation. It's a pleasure to be here today and to talk about what we've been doing recently. So, one thing I should say before I start is about the slides. So, those are not really slides, those are figures, if you have noticed already. It's a PDF file with a bunch of figures, but I thought it would be really useful for me when I'm talking about this topic. I can refer to those figures, and there are numbers in there, and I will use those numbers. Okay, so the work I will be talking about today has been done as part of a collaboration, international collaboration in cosmology, which I've been one of the founders and leaders of this collaboration. It's called COMPACT, which stands for Collaboration for Observations, Models, and Predictions of Anomalies and Cosmic Topology. So I'm going to tell you today what is this collaboration about, and what we do, and what are our motivations, plans, and all that. So the topic is about the topology of the universe. And the topology of the universe, basically, I'll tell you more about that, of course, is about the global shape of the universe. Okay? So what I will tell you today about is basically why we want to know the topology or the global shape of the universe, and how we want to determine it using cosmological observations. Okay? So before I start really talking about topology and all that, just give you some ideas. So as you all know, on Earth, every straight path is a great circle, which is around the planet, right? So the question then is, do any straight path through the universe similarly loop back to where they started? Okay, that's basically something that you'll see is related to topology. So basically, cosmic topology seeks answers to questions like whether space is infinite in all its dimensions, or venturing off in some directions, we would, like as on the surface of the Earth, eventually return to where we started. Okay, so that's about connectedness. It's about how you go from one place in space to another place. So rather than stretching to infinity and beyond, the universe may have a topology that can eventually be mapped, and that is really exciting. We may be living in a donut, as Cecile was also telling you. So it sounds really weird, of course, but that could be the shape of the entire universe. We still don't know. And this is just one of the many possibilities for the shape of the universe. And what we're really doing, we're trying to find that shape. Okay? And with that very short introduction, I'll start going through this more step by step. Of course, I'll try to be not much technical. And later on, I'm very happy to discuss things and answer any questions if you have. So, of course, the first question then is, what is cosmic topology? Okay. So I briefly told you, but basically cosmic topology is a field, is a subfield of cosmology, and it is the study of the overall shape of the universe. It's mainly about global features of three-dimensional space, and these features, for example, include the connectedness of different regions. But it also includes some local geometrical properties, such as curvature, even though curvature is a more like a local property that changes from place to place in the universe, but still the global curvature, in a sense, we can define, and that's related to the topology as well, as I will tell you more about it later. So some of the examples of the questions that we want to answer when we are studying the topology of the universe are the following. So, for example, is a space finite or infinite? Okay. Is a space what we call simply connected or multiply connected? And I'll tell you what I mean by those. Is a space smaller or larger than the observable portion of the universe? Okay. So these sorts of questions are the ones we are trying to answer. And I'll give you some motivations for those later on, why these are very interesting questions. But before that, let me tell you more about topology itself, what I mean by topology. Okay. So topology is the mathematical study of the properties of objects, those properties that are preserved through deformation, twisting, and stretching of the objects. Okay. So if you take an object and change it, by deformation, twisting, and stretching, then you preserve the topological properties of the object. Okay. One thing that is not allowed here is tearing. All right. So there is this mathematical joke. Maybe if you can look at figure 1 in the document that I sent you, there is this mathematics joke. The joke is, the question is, what is a topologist? And the answer is someone who cannot distinguish between a donut and a coffee cup. Okay? And as you see in that figure, a coffee cup or teacup or whatever you want to call it is basically equivalent or equal to a donut topologically. The reason for that is, as you see on the right hand side of the figure, you can take this cup and change it slowly, continuously, through this procedure I told you, like deformation, twisting, and stretching, and then you can change it slowly and continuously to a donut, right? So you notice that one thing that is preserved here is the number of holes in that object. So a donut and a coffee cup both have one hole. This is a topological property. So you cannot change that through this procedure. Okay. So for me, a donut and a coffee cup are the same as a topologist. Okay. So in summary, the topology of an object specifies how its parts are connected, basically. A donut has the same topology as a coffee cup, and the hole is is equivalent to the handle in this case, right? So you can remold a donut into a cup, like a coffee cup, without tearing it. Similarly, a sphere, cube, and banana all have the same topology because none of them has any holes, right? You can take a sphere, change it to a cube or a banana or shapes like that, and you are not changing the topological properties of that. So let's look at figure 2 that I sent you. You see four kind of geometrical objects in there. These are two-dimensional objects because these are surfaces. We're talking about the surfaces, and surfaces are basically two-dimensional. So if you look at these objects and investigate the properties of their two-dimensional surfaces, then we notice that actually it is easy to see that one cannot start from any of these four objects and change it continuously to another one by only deformation, twisting, and stretching, right? Start from the sphere, you cannot make it like a torus, or the double torus, or a triple torus. So, and the reason is that these procedures keep the number of holes unchanged. Therefore, we say that these objects have different topologies. And if you want to see a better example, look at figure 3. You see a lot of objects that you can find around you. Let's, for example, pick up one of these objects. For example, that chair that I put a circle around. And that chair, you see that it has actually two holes, right? Therefore, it has the topology of a double torus, right? Like the third one in figure 2. So a little bit like more mathematical way or a different way to show different topologies for a surface, a two-dimensional object, is through the diagrams you see in figure, I guess, 4. So in figure 4, you see some diagrams. Let's look at the first one, on the left, top left. So you see there are basically, first of all, each dashed side shows an infinite or non-compact dimension. Okay, so when you have a dashed side, so it means that if you go there, you continue going forever. So you're not going back to anywhere. So each solid arrow there shows a compact dimension, which is identified with the opposite side. Okay, so which means that, for example, in the second diagram, top second one, you see there are two arrows like parallel, A, B, B. So it means that if I move to the right, basically come back from the left, right? Because those two sides are identified. They're the same. So the first diagram shows a disk or plane or infinite plane, basically, because there is no border, there is nothing, there is no identification. So each direction you continue, you go forever. But the second one, you identified one of the directions, or basically two sides. You compactified one of the directions, and that generates a tube or a cylinder, right? Now, for example, look at the third one. The third one, first of all, the two sides are the same, like basically identified, left and right. But top and bottom basically are basically identified as well, and that means that basically A, B, C, D, all these points are the same. So A. No matter where you go, if you go if you move towards right, you come back from the left. You go up, you come back from bottom, and that means that the whole thing is compactified, and that's a torus. Okay? And you can do other things as well for that. So in cases where an arrow changes direction, for example, you can see in the second one from basically second row, second column. You see the arrow, an arrow actually changes direction on the opposite side, which means that when exiting from that side, there is a twist, which means that right-handed objects become left-handed and vice versa. That is what happening when they enter the space again. Okay. For example, the one we call Mobius strip has that property. So before I show you some of these examples, so let's just focus on that torus one. So if you look at figure 5, unfortunately, the left figure was supposed to be like a little movie showing how you can actually compactify. So you start with this infinite plane, and if you identify two sides, like make a tube, then basically you're compactifying in one direction. And if you then identify the two other sides as well, then what you're making is like a torus. And all these surfaces, an infinite plane, a torus, and the tube, they are all geometrically flat. You can show them, so they're all flat, which means that the angles of a triangle add up to 180 degrees. And maybe that's good news for flat earthers. You can even have a flat Earth, which is compact, so it doesn't need to be infinite. So that's the Earth you're seeing. So that Earth is actually flat, but is like a torus. So we can now look at, for example, figure 6. You see two other shapes. The one on the left is a Mobius strip, and that's the one I talked about before. So one direction is compactified. So if you go around that, you need to go like two times to get back to yourself. Otherwise, just going once, you change your handedness. So you need to go twice. And then there is another one where you compactify also the other direction, the third one. Well, the second one, sorry, not the third one, the second one, and then you get a Klein bottle, and that's the shape you're seeing. So that has the same property. In one direction you go, and you basically change your handedness. Okay. So now you kind of got the feeling what I mean by topology. But then the next question in topology is what we mean by simply connected topologies versus multiply connected topologies. So another name for a simply connected topology is trivial, because the name is trivial topology. A trivial topology is a simply connected topology. It's just a name. And we call multiply connected topologies also non-trivial topologies. Okay. So what is a trivial topology? So a space has a trivial topology if it is path connected, meaning that you can connect every 2 points within the space, and every path between the 2 points should be continuously transformed must be any, that, what I mean is that that should be one of the, that's basically one of the requirements, that these 2 points, that every path between the 2 points can be continuously transformed into another, any other such path while preserving the 2 endpoints, okay? So you start with one path and you change it continuously, you should be able to generate another path. So every path can be mapped to another one. If a space has that property, that has a trivial topology. So of course, when we say multiply connected, that means that it's not simply connected. So, but there is another way of seeing the simply connected space, the property of that, or like topology of that. So a space, simply a space with holes, has a non-trivial topology. Any space that has a hole in it. Okay. So any loop that encloses, the reason is that any loop that encloses one or more of the holes cannot be contracted to a point without exiting the region, right? So, for example, look at figure, I guess 8. Yeah, figure 7, by the way, was the one I was talking about, the path connected thing. So the 2 points, and you see 2 paths there, and they can be, one can be mapped to the other. So if you look at figure 8, you see a sphere, and you see the circle, and a sphere is simply connected because every loop can be contracted on the surface to a point, as you can see in that figure, right? You start with a big circle, and you can contract it to a point. And you can do it for all the closed circles, right? So that is showing, that's another way of seeing the trivial topology of this space. Now, if you, for example, look at figure 9, you see an example on the left. You see an example of the space, 2-dimensional space surface with 3 holes in there. And obviously, that's not simply connected, because there's an example, like a circle around the hole there. There is no way to contract that circle into a point, because there's this hole doesn't allow you to do that, right, continuously. So, and obviously, a simple example of that is a torus on the right, and you see there are 2 circles, one red and one blue. You see those circles, you can never contract into a point without leaving the space, okay? So again, you get a feeling what I mean by trivial or non-trivial topology, or simply connected and multiply connected topologies. Now let's get to 3 dimensions. So that was all about 2-dimensional cases, right? So the universe is a three-dimensional space, and there is nothing wrong with that also having similar topologies or global shapes. So global shapes are not only about 2-dimensional surfaces, about any surfaces with any number of dimensions. For example, look at figure 10. On the left, you see like a box. And this box, you cannot see it, but that's just an example, because the universe can be like a 3-dimensional torus, okay? Here in this example, the universe is flat, right? And all 3 dimensions are compact. It is like a hall of mirrors, where lines of sight within the 3 torus form closed loops that return to the viewer. So everything appears to repeat infinitely in this example. So I can give you another way of seeing that. Let's talk about a very simple example. So we can assume that the universe is like a 3-dimensional version of an old-time video game. For those of you who remember those games, where leaving the right side of the screen would see you basically popping in from the left. Okay, that's the figure you see again, figure 11. This is like one of these old video games, and that's because left and right are identified, and top and bottom as well. So that's what it is. Now, a toroidal universe is a 3-dimensional version of this game with a cubic screen rather than just like a 2-dimensional screen, where not only are the right and the left faces identified, but also the top and the bottom, and the back and the front are identified. We call such a cube the fundamental domain of the universe, by which the covering space or an infinite space can be tiled. You can put this together and cover the entire infinite space. And this generates clones of every object, including us as observers in this huge covering space. Okay, so that's an example of a three-dimensional universe, which is a torus or a donut, a three-dimensional donut, right? So let's look at figure 12. Here, the illusion of the universal, here you can see the illusion of the universal covering space, the whole space. So in the case of again, this is a two-dimensional example. In the case of this two-dimensional toroidal space, the fundamental domain, which basically represents the real space, is the interior of this gray rectangle, okay? And the opposite edges of this rectangle are identified. This means that if you have an observer O that is seeing rays of light from the source S coming from several directions, of course, S and O both are in this fundamental domain because that's basically the real universe. They have the illusion, these observers, of seeing distinct sources like S1, S2, S3, all of this, okay? Because these are just clones of the same universe. The reason is that the light basically goes from different directions and they come back to you in different ways, and you can see different images of that. So these are all distributed along the rectangular, these are all distributed along a basically regular canvas, which covers the covering space. And this covering space is an infinite plane. Another example on the left you see of that figure is again this torus, or two-dimensional torus, or donut. So you see that red point is, for example, where we are, and then light can go around the universe and come back to us. So if you wait enough, you can even see an image of ourselves, right? And it can go also in different directions. So this universe will basically give you images of yourself and other objects and so on. So in addition to topology, there is another aspect that is very interesting for us cosmologists, and that's the curvature. And I told you before. So in his theory of general relativity, Albert Einstein showed that a space can be curved by massive objects. That's basically the foundation of the general theory of relativity. This space that can be curved by massive objects creates the force of gravity. Basically, that's the theory. Okay, so really, what is important here is curvature. So these possibilities can be distinguished by simple geometry. Imagine space as, again, two-dimensional, like a sheet. So you can look at the other figure, the next figure, figure 13. So imagine a space as two-dimensional, and rather than having all three spatial dimensions. On a flat sheet, the angles of a triangle must add up to 180 degrees. That's the definition of being flat, right? But on a curved space or curved surface, like the surface of a sphere or a saddle, that's no longer the case, right? As you can see in these examples. So yeah, one is like a sphere, what we call closed universe, then we have a flat universe, and we have an open universe, which is negatively curved, like a saddle. So by comparing the real and apparent sizes of these distant objects, such as galaxies, astronomers can see that our universe as a whole seems to be as close to flat as we can measure. Okay, this is the state-of-the-art result. So we have been trying to measure the curvature, and so far everything has been completely consistent with a flat universe. It's like a flat sheet popped with little dimples, where each star deforms the space around it. Okay. Now, okay, so the universe can be flat, right? Because so far observations are not giving us any reasons to believe that it's not flat, even though it can also be curved, but is also considered flat. Now let's look at a flat universe. So we have a three-dimensional universe, which is flat. What are the possible topologies for that? So mathematicians have shown that a flat universe can have 18 different topologies. This number 18 has been proven, okay? So that's basically a mathematical theorem. And 17 of these topologies are non-trivial or multiply connected. So look at figure 14. You see all these 17 non-trivial topologies for a flat universe. We call them E1 through E17, and E18 is just a trivial universe, trivial flat, which means like it's infinite and flat and so on. So now, the nice thing is that, so first of all, the ones on the left, which are 10 of them, they all have three compact dimensions. For example, look at E1. E1 is a simple tree torus. So you can look at the doors. So if you exit from that side, from the back, you come back, and that's and the same thing for the other directions. Then we have, for example, E3. Okay, historically we call that E3 rather than E2, but anyway, that's called a quarter turn space. So you come back, but you turn by 90 degrees, right? And then you have other complicated ones as well. I'm not going to go through this, but there are different 10 compact, fully compact non-trivial topologies. Then you have E11 through E15, and these all have two compact dimensions. One of them is infinite, but the other two are not. So these are called like chimney spaces. And then you have two other cases, which we call like slabs, and they only have one compact directions. Okay, so these 17 are all okay. And some of these topologies also you should notice that are non-orientable, what we call non-orientable, which means that if one exits from one side and enters from the other side, their handedness will change. The same thing has happened to the Mobius strip or like a Klein bottle and so on. Which means that one becomes the mirror version of themselves when they come back. Okay, so you have to go at least twice to get back to get the same handedness that they started with. These 18 topologies are only some of the possible ones, but if the universe is not flat, which means if it has a non-zero curvature, then one can show that there are an infinite number of possible topologies for the universe. It's not anymore 18 or a finite number, it's infinite, okay? And even for the case, for the case of a positively curved universe, these topologies have been classified, even though there are infinite of them. There are infinite of them. But for an open universe, like negatively curved, they are not even classified yet. It's just hard, okay? Okay, so you got a feeling of what we mean by topology of the universe, and you want to basically search for that. But let me then tell you why the search for cosmic topology is interesting and important, okay? So first of all, this is a very old question, because humans always wanted to know if the universe was finite or infinite, okay? This is a very old, maybe 10,000 years old, I don't know. It is also a very important question for cosmologists. So when you study something, you want to know its shape. I mean, that's one of the natural things to know about the thing you are studying. And cosmologists like me basically study the universe, so they want to know the shape of the universe. That's a very obvious question to ask. Well, of course, that's not the only reason. It is actually has been shown that it is much easier for a finite universe to be created through an early universe process. There are theoretical models in which the probability of a universe with the volume, for example, V, for that to be created is something like exponential to power minus V, which means that the smaller the universe, the higher the chance for it to be created. Okay, so finite universes are more likely to be created. And measuring the topology of the universe would definitely be a truly remarkable physics accomplishment. Because we would know the full extent of space and we would map the entire universe. It's like knowing, everything on Earth, right? Even having like some kind of like a version of Google Maps where you see everything in the universe, not just on Earth. So measuring the topology of the universe would also be okay. So if we discover an non-trivial cosmic topology, that would require significant rethinking of the earliest epoch of the universe. In cosmology, we have many theories for that, but we would need to really sit and think about them again. Why? Because we would know that if there was, for example, an inflationary epoch early in the history of the universe, that's one of the parts of, that's one of the elements of the standard model of cosmology, where we think the initial conditions of the universe have been set through a period of expansion of the universe, which was very fast, and that's what we call inflation or cosmic inflation. But we would know that if we discovered a non-trivial topology, that could not have lasted long enough to inflate the scale of topology. Then cosmic inflation would also not be the explanation for the approximate homogeneity of the universe beyond detection. So this is a theory that originally was designed or invented to explain why the universe is very homogeneous on larger scales. But then, I mean, if topology is detectable, I can tell you more about that later, but that would, make it hard for inflation to explain. And the discovery of the non-trivial topology would have also enormous implications for the theory of quantum gravity. So there are certain theories of quantum gravity that predict topology changes in the early universe. And obviously, if I tell you that the universe has a particular topology, for example, this volume and so on, with this shape, then all the fundamental physicists, people who work on quantum gravity and so on, they should tell me where this universe comes from. So that has really huge implications for quantum gravity. There is another reason as well. So for those of you who might know what string theory is, string theory is one of the fundamental theories in physics, and maybe it is already telling us that the universe has a non-trivial topology. Why is that? Because in string theory, if you know, we have at least 6 extra dimensions. We cannot live in a universe with only 4 dimensions, like 3 spatial and 1 time. We need at least 10 dimensions, so 6 of them are just extra spatial dimensions. And these 6 extra dimensions must have been compactified to very small sizes because we do not see them, right? So now the question is, if we need to compactify 6 dimensions, why not compactify 3 more, right? So maybe that's again a hint that the universe has a compact dimension or a compact, form, or basically it has a non-trivial topology. And then finally, there is these were all like theoretical motivations, but also there is this growing evidence that the universe is not statistically isotropic. That's a technical word, which means that physics is not the same in all directions. This is an assumption that is part of the standard model of cosmology, but many people have shown, and recently us as well, in another set of papers, that it seems like this is not true. The laws of physics are not exactly the same in all directions. And topology is a very natural way for anisotropy to creep into our universe. We have observed the violation of statistical isotropy mainly through the so-called anomalies. These are some anomalous properties of the cosmic microwave background, the CMB, which is the very faint glow of heat left over from the Big Bang itself. And basically, nowadays it fills the cosmos with microwave radiation. So by studying those properties, we have seen some anomalous features on larger scales. And the relevant physical scales for these anomalies are very large. And topology breaks isotropy because the direction of a closed loop around the universe is different than a direction in which there is no closed loop, right? And topology is one of the few ways in which one can imagine the statistical isotropy being violated on these larger scales in the complex ways that the evidence basically suggests. Okay, so that's one of our reasons, one of our motivations for actually studying these anomalies, and that was in the also in the name of the collaboration. And maybe those are already telling us that the universe has a non-trivial topology. Okay. Finally, how to search for cosmic topology with all these motivations around that. So topology, as I told you, is about connectedness and global properties of space rather than its local geometrical properties. So a non-trivial topology has a bizarre implication. Okay? What is this implication? If the universe has a non-trivial topology or is basically multiply connected, then there are closed loops in the universe. So if one starts at a point in space or the universe and move in a non-finite direction, then they will eventually go back to where they started, right? So that's basically the implication. This is true also for light rays. If you could look out across all the universe, which would require the speed of light to be, of course, infinite, you would see endless copies of yourself in all directions, like a three-dimensional hall of mirrors. But other and more complex topologies are violations. So let me say it differently. So the other complex topologies basically will give you similar effects, where, for example, the images would appear slightly shifted, maybe. You re-enter the box in a different place, or perhaps twisted so that light becomes left, and so on. But anyway, so still you see all these images. Therefore, I mean, based on this, one obvious way to search for topology is to look for topological clones, what we call topological clones, which means that we look for pairs of identical astronomical objects on the sky. However, the main issue with this method is that clones would be seen at different ages, from different perspectives, and along different lines of sight, because they're coming from different times, and light takes time to get to us. So it is difficult to know which objects are clones of which objects. So you can see this, what I was telling you in this figure, the next figure, figure 15. In this example of two-dimensional universe, you see if you have a galaxy, the light can get to the other galaxy from two directions. So that's why you see it like two different directions, right? Okay. However, there is another method. So the other method is by searching for matched circle pairs in the cosmic microwave background, which I told you that the light left over from basically a Big Bang. This is a sort of a map of what the universe looked like at the earliest stage that we can still observe today. And that's imprinted on the sky all around us. So the CMB photons all come from approximately the same distance from us, which is around 46 billion light years, and all from the same cosmic epoch. Now let's look at this other figure, next figure, which is figure 16. Look at this figure and imagine that the gray region is a two-dimensional universe whose left and right sides are identified, okay? You can go to infinity from above or below, but the left and right are identified. So imagine that like observers are sitting at the center of the region, like this. This is what I've shown by a red point, and we are observing the sky, the CMB sky around us. That circle, centered exactly at that red point. If the diameter of the CMB is larger than the size of the compact dimension, then the CMB skies that are nearby clones that I'm showing by this blue points will interact with our CMB sky, right? They also see like circles around themselves, but these clones are basically us. They are the same things, which means that we should see identical points on the CMB sky, because you see some of these are intersecting, and that means that there are identical points in different directions. For a three-dimensional universe, this was a two-dimensional example. For a three-dimensional universe, what happens is what you see in the next figure, which is figure 17. One can show that if the universe has a compact dimension, then and if it's small enough, the CMB is not a circle anymore. It is a sphere. First of all, sorry. If the universe is two-dimensional, the CMB is not a circle, and it is a sphere, which means that if the universe has a compact dimension, and if the size of this compact dimension is not larger than the diameter of the CMB, then we should see identical circles on the CMB sky, right? Because there are now spheres that are intersecting. Of course, this was proposed by one of my collaborators in 1996 and some other people. And of course, cosmologists have searched for such matched circle pairs in both WMAP and Planck datasets, which are the main CMB experiments we've had. And I myself have been a member of the Planck collaboration and work on this stuff. So people have searched for this. Cosmologists have searched for these circles, matched circles, but I have not found any identical circles. And this has taught us that the distance to our nearest topological clone is at least 98.5% of the diameter of the CMB, which means it's around 90 billion light years. Why not 100% if you haven't seen any circle? Because when the circles are very small, then we have some statistical errors and uncertainties. We cannot really look at very small circles. So there is still some, of course, room there, but almost 100%. So that's basically what we have learned. So the distance to our nearest topological clone is at least around 100% of the diameter of the CMB. Now, this is what we have learned, but now that we know that the universe is not sufficiently small to create identical circles on the CMB, then the question is, how can we search for the topology of the universe? There are no circles. What else? So the lack of matched CMB circles is what tells us about the length of the shortest closed loop through us, but it does not tell us about the length of loops through other places in the universe, right? It's only about us. So if the CMB anomalies are due to cosmic topology, then the length of the shortest loops through us should not be more than about 20 to 30% longer than the diameter of the CMB. The reason for that, we showed in our paper. You can see this is a bit more technical. If you want, I can tell you later. But we know that if cosmic anomalies are because of topology, then the universe cannot be very big, maybe like 20, 30% larger than the diameter of the CMB. It is a sphere with radius equal to the distance that light has traveled in the history of the universe. So now look at the next figure, figure 18. So we know that the universe is filled with radiation, which is the CMB, and also different types of matter, like galaxies and other cosmic structures and so on. So now, if you look at one of those cubes where I put the CMB in there, so there are no circles because the CMB is smaller than the size of that cube. But the non-trivial topology does something to this universe. Even if there is no circle on the matched circle, basically there are no matched circles on the CMB, but a non-trivial topology discretizes and correlates different modes of these structures that you see, different modes, everything that is inside this box. So by studying these modes, we can know what topology the universe has. And these modes are like acoustic modes. And the question that we are basically asking is similar to asking, can one hear the shape of a drum? Okay, this is a mathematical, so this was a title of a famous mathematics paper from decades ago. So the question is, can one hear the shape of a drum? If you listen to a drum, can you actually guess the shape? So in the same way, one may want to infer the shape of a drum. So basically, let's do this this way. So in the same way, one may want to infer the shape of a drum by analyzing the sound waves, which means by studying their discretization and correlations. We hope we will be able to infer the shape of the universe by analyzing all the cosmic structures inside the universe, okay? All different modes. So since there are complications in the cosmological data, like instrumental noise and contamination by astrophysical objects and so on, the question really becomes, can one hear or infer the shape of a three-dimensional cavity with imperfect ears, okay? So let me tell you that anticipated data from upcoming large-scale structures like Euclid and the SKA observatory and the CMB experiments like next generation, like Lightbird and so on, will probe in detail much of the spherical volume of the observable universe back in time to its first millennia. Sorry. And this is crucial improvement over the CMB, which principally probes the surface of that sphere, right? And it's also crucial improvement over existing surveys that are far less complete. This should vastly improve our ability to identify and characterize the acoustic modes. And remember that a non-trivial topology discretizes and correlates modes for any structures in the universe. This includes the CMB, distribution of galaxies, and the other things that we call, for example, 21 centimeter intensity maps, and so on, everything in the universe. So we can use and combine all of these data sets to enhance the topology signal. As the very last thing I want to tell you, let me emphasize that if topology is the physical cause of the CMB large scale anomalies, then the CMB must contain detectable topological information, right? And since we have shown that such information in this paper, for example, in our paper, we have shown that such information is absent in the CMB data if the distance to our nearest clone is more than approximately 120% of the diameter of the CMB, then that means that cosmic topology might be within reach. And that motivates us to harness whatever cosmological information can be gathered to determine the topology of the universe. And of course, the risk is very high, as we may merely extend current limits incrementally, but the potential reward is really great, as we may map the entire cosmos, right? And the final figure you see, which is the logo of our collaboration compact. So this is what we have started to do through this international collaboration called Compact. Again, that stands for Collaboration for Observations, Models, and Predictions of Anomalies in Cosmic Topology. And the objective of Compact is to create and implement the necessary computational and statistical inference infrastructure to exhaustively search for the topology of the universe using all the existing and future cosmological data. So in summary, our goal is to discover the topology of the universe or show it is beyond all possible data to do so. Okay? And this is a 5 to 10-year program, which has just begun. The search for topology has been renewed after about a decade. After about a decade long hiatus, and basically, hopefully, we will detect cosmic topology, and therefore we'll be able to understand the origin of the anisotropy of our universe, and also get a glimpse into the processes that are responsible for the original emergence of our universe. There is a great deal of work to be done, researching exhaustively for the topology of the universe, and also understanding the implications of topology on the physics of the early and contemporary universe. So we are super excited about all this, and let's see what happens in the next few years. I'm sorry I talked too much, but I'll stop here, and I guess we should get to the questions and discussions. Thank you.
Yeah, thank you so much, Yashar. It was really a very, very interesting presentation. And thank you for the slides, really great slides
No
here.
worries.
I would like to announce to the audience that we are opening the floor for questions. Just raise your hand. If you have questions, we will bring you up to the stage. And you can also write your questions here at the room chat. So, for the sake of the people who just came in, I would like to have a shorter reintroduction of our guest speaker here. Dr. Yashar Akrami is an assistant research professor, Ramon Ika Fellow of Theoretical Physics, um, in cosmology, especially at the Institute of Theoretical Physics, IFT UAM-CSIC in Madrid, Spain. He is also an adjunct assistant professor of physics at Case Western Reserve University, CWRU in Cleveland, Ohio, USA, and is a long-term visitor at the Imperial College London in the UK. He was previously a Richard Morrison Fellow in Cosmology at CWRU, and before that, he held a junior research chair position at the International Center of Fundamental Physics, ELPEN's École Normale Supérieure in Paris. And before Paris, Yashar worked at the Lorentz Institute of Theoretical Physics, Leiden University in the Netherlands and the Institute for Theoretical Physics, Heidelberg University in Germany, and the Institute of Theoretical Astrophysics at the University of Oslo in Norway. Yashar has received his PhD from the Oscar Klein Center for Cosmoparticle Physics in Stockholm, Sweden. So yeah, we have here Eric, one of our regular moderators here in Quantum Photonics, who also helped us in the starting of the club, who came on stage. And I would just like to react to just a small reaction for now to your presentation because yeah, I think it's indeed very fantastic. And I had also posted the announcement of our event in my Facebook groups, which has a lot of people who are a niche group truly interested in physics and cosmology, and it has had a lot of reactions, even just the shares of the posters. So I think you have to come with me next time to talk about your work and also about the work of your group in Facebook Live, the work of compact collaboration, because the people there have a lot of questions and also have a lot of insights about your even just the popular paper or the abstract that we had shared. So thank you so much. And myself, just before you gave this talk, I was very interested because it reminded me of string theory, and indeed, and also about the parable of the blind man and an elephant who is looking at the elephant in different points of view, and they all have different interpretations of the elephant, but yet they are looking at it. And yeah, just like similarly in some interpretation of string theory, that's just like it. And I thought that this research tells a very good story aside of giving a great contribution to our understanding of the universe. So yeah, thank you for sharing this with us. So any comments?
Thank you so much, Cecile. Yeah, it will be my pleasure, of course, to talk about it again somewhere else as well. And thank you so much. Yeah, I mean, we are excited about what you're doing. I'm very happy that that was hopefully interesting to you guys as well. So yeah, thank you so much.
Yeah, thank you. I think I would like to ask other questions, but I'll save that for later because Eric Ayo is here on stage. And hi Eric, long time no
Hi.
see, and thanks for coming on
Yeah.
stage.
Awesome talk. Really appreciated this kind of like, you know, surprising Saturday treat, as it were. Like I was trained as a differential geometer, kind of string theorist, went to biophysics. And so, first of all, I love that the presentation had almost like no equations because the it's like one of those things. The more advanced the math, the kind of less there is kind of an equation need, at least when you speak to the general public. I wanted to know if you had any insights on how to communicate some of those more exotic topologies, like the E1 to 10, and then 11, and then the 2. If you had any intuitions for folks on how to think about that, because like perhaps you and I know how to think about it mathematically, but to think about what it means to have a torus within like our space-time or something like Mobius strip, that's one thing. And then perhaps how did this more naturally come to you? Was it something that you thought about as perhaps a child and then revisited sometime later? I'm curious what that process was also like, because this is kind of one of those, I would say it's like a big result, but it seems to have been kind of a mountain that probably took a while to climb. So I'd be fascinated to hear if you have anything to share about that.
Thank you so much for the questions. And yeah, so for the first one, yeah, it's a bit difficult to really explain or describe these topologies in a non-mathematical way. The best I could do by basically, you see this figure, what was that, 14? So you see this fundamental domains, and simply that's what is happening, right? So if the universe has any of these topologies, that's the universe. So that's the fundamental domain. There is nothing beyond that. So it is very hard to imagine, as you definitely, I guess you confirm, like a three-dimensional torus, for example. We can all imagine a two-dimensional torus. It's easy because you're seeing it all every day. But a three-dimensional one, no, not really. So yeah, so mathematically, of course, I can tell you how we do it. And if you look at our technical papers, based on all these generators, all this, vectors and so on, how you change if you go from fundamental domain to a clone, and exactly to these vectors and so on. So these are all mathematical descriptions, and I don't really think that's here is a place to talk about those. But non-mathematically, yeah, that's the best you can see. So these examples of like doors. So when you exit from one face, you basically enter immediately. So you're not getting out of the universe. The universe is just that. There is nothing else. The whole universe is just that, right? So it's very similar to that video game that I told you before. So it's just the entire screen will be the entire universe.
Can I ask a question? Can I just interrupt? So for that question, so when you extrude out away from the page, let's say we're talking about, let's just say E1. So you extrude out away from the page and then wrap it around so the doors match. But you may have to wrap it around and twist it to make the doors match. So that's kind of what I'm talking about. Like you can pull out or extrude, and so that allows some people to perhaps better imagine that. Because I remember when I saw these kinds of graphs in differential geometry, it was kind of tough for me to think, oh yeah, this is just the boundary condition, and here's the asymmetric boundary condition on the other side. And of course, if one flows through the other, and you pick up a rotation or whatever. So yeah, and then I guess the final question was kind of like how you came to be studying this. Was there like
I was
gonna say like you probably thank you.
Right. I was gonna answer that question next, but yeah. So for the first one, you're right. So first of all, let me emphasize that you need this picture of like twisting and like putting these things together and so on only when you embed this space into a higher dimensional space, right? So you cannot imagine a two torus. You can imagine a two torus because you live in a three-dimensional space. So that's how you can imagine that, and that's exactly what I was showing. So you identify two sides and you make a torus or like cylinder or whatever. So yes, if you want to see something similar, then you have to go to at least 4 dimensions. In 4 dimensions, you can say, okay, if I want to embed this three-dimensional space into that space, in that 4-dimensional one, then yes, I can then give it some curvature, which is what we call extrinsic curvature, not intrinsic, because intrinsic these are all flat. Then yeah, you can say that those two doors are basically just identified somehow. They're connected through these 4 dimensions. But what I'm trying to emphasize here is that the universe does not need to be embedded in a higher dimensional space. Okay, mathematically, the universe can be just that, only a 3-dimensional space, and it's all fine. So these are just boundary conditions, as you mentioned, and boundary conditions can be there. So you don't really need to imagine that this universe is like curved within a 4 or 5-dimensional space or something. So you can do that. You can think about it that way, but you don't have to. So if the universe is just this and nothing beyond it, or nothing in other dimensions, then unfortunately that's the only way to think about it, just boundary conditions. And I don't think there is any other way, because you don't have any higher dimensions to imagine that within that space, right? And let me quickly answer your second question. I've been interested in cosmology, different aspects of cosmology, and this is not the only thing I'm doing. I've done lots of things about the early universe, about late universe, dark energy. I did some dark matter in the past, theories of gravity. Also, I want to understand the universe. That's my goal. I'm a cosmologist, and cosmology is a field where you see all of these things are related. Okay, so the question of topology by itself is very interesting. As I gave some motivations, has always been intriguing to me because I wanted to know the shape of a space. If you talk about general relativity has 2 interpretations. One is geometrical, which is the conventional one, just the traditional one. That's what people teach. I teach that in my class. General relativity. That's that picture, and then that means that the space has a shape. Space exists. Space is something with curvature and so on. And obviously, you can ask about the shape of it and so on. So this is really intriguing. It has always been intriguing to me. But also, there is another interpretation of GR. General relativity, which is completely different. There is no curvature or nothing in there, but I don't want to get into that. But topology can also distinguish between these 2 interpretations. So if I detect the shape of a space, then it's hard to assume that the universe, so that the theory of general relativity is not about space; it's about I don't know, some fields that are related to each other somehow and so on. So that's definitely. But yeah. So I have been always interested in that, but recently more and more because I feel like we are seeing this is related to the discussion of cosmic anomalies. We have been seeing a lot of anomalies on the sky, things that do not really we do not really expect them from the standard model of cosmology. And people have worked on those things for like probably 20 years now at least. And I was one of the main people as well within the Planck collaboration that studied these anomalies in many papers and so on. So I was always looking for an answer to this question of anomalies. And cosmic topology probably is our best bet at the moment. So at least to me and my collaborators. So yeah, so there are different reasons for being interested in topology. First of all, I want to know really what the universe is about, like what is it, what's the shape of it, how big it is, and so on. This is just a question, curiosity. But also there are lots of connections to fundamental theories, to observations, to all the things we are seeing on the sky. We want to understand about other things. So if we change the standard model of cosmology in any way, then that might teach us something about other things like dark energy, like the early moments of the universe. So there are so many reasons why I'm interested in this question, because I think this is very fundamental, and general relativity does not specify the topology of the universe. General relativity is a bunch of differential equations. Differential equations are local equations. They don't care about boundary conditions. We can impose the boundary conditions and then solve the equations. And the question is why? Why did we choose just three simple cases? Einstein actually didn't choose the three simple cases at the beginning, but eventually it became more like that. So if you go back to many decades ago, like Schwarzschild and even like De Sitter, those people, they were considering these topologies. So we have infinite possibilities. Why only these three obvious ones? So this is a very natural question to ask. So I don't know if I answered your question, but yeah, there are so many reasons.
Yes. Yeah, you did. I really appreciate that it was like a 20-year kind of thing. You're like, hey, I chipped this this iceberg away a while ago, saw these anomalies, and then you had this kind of result. I don't know how else to get people excited about topology, because I'm excited just listening to you discuss this and kind of blow my mind, because it's obviously one of those things that kind of was missed. And so if you were to recommend a book, like this is kind of, a cheeky question, maybe offhand, but if you have a recommendation of a book for folks to look at, like maybe your favorite topology book or a book that you felt, or maybe a paper, something like that, that was helpful to you from someone else, kind of, standing on giants' shoulders and all that, that would be also perhaps something that would allow people to engage with the content and perhaps follow up with you. Thanks.
Absolutely. So thank you. So yeah, I mean, maybe I will send some of the some links or something or names of the papers or books to Cecile. Maybe she can then add them to the
awesome. Thank you.
I don't know, at some point. Yeah. Sure, of course. But I should say that most of these papers and books are very technical, unfortunately, because it's hard to write. Maybe at some point we will do it, but at the moment these books are very technical. But I'll try my best to find things that could be useful to you.
Yeah, because most of the topology that I learned was not from a textbook; it was like from classes, and the professors just had their own notes, right? Like they would just have like here's a book that I referenced, but actually you should learn it kind of my way. And perhaps mathematicians learn things a little bit differently than physicists and standardization and all that. But just as a reference for public folks. So thank you for that. And I see that Kevin has come up, so. Perhaps we can ask Kevin about his question or comment, Cecile.
Yeah, thank you, Eric. So, yeah, thank you for coming here today. As I said, we missed you here in Quantum Photonics. So, we have Kevin who just came up. So, yeah, I'd like to give the mic to Kevin now. Welcome, Kevin.
Yeah, thanks a lot. I don't have much on this. The best I can think of is, I used to work at Atari. We had another game called Combat. Where you get knocked. It's tanks. You know that, right? You get knocked out of the wall. Yes. Yeah. So then you come back to the other side, and that's perhaps the first feature of games. You call it a feature. This just left it in. I didn't work there till the 90s, but but the best thing I can think of is if it's like an old time game, where you get to the border and then you come out somewhere else. I can think of physical, models where so perhaps you get maybe there's white holes and black holes and quantum loopholes and physics and stuff like that, and exotic properties on the at the edges, is what I can think of. And then so and also in just different physical models, you get to the edges and you get stuck around, you get because of different forces, perhaps exotic forces, and so you get sucked around, and then randomly you get sucked back in, from another area. So that's from the fringe, so that's some of the things I can think of right now. And thanks for this. I'd love to dive into this. It's awesome for a Saturday morning, waking up. Thanks.
No worries. Thank you so much. So, okay, so there were two questions here. So the first one about black holes and wormholes and all that. Yeah, I fully agree with you. Those are also topological defects. Those are basically topological properties within the universe, but they are different. Okay, so here I'm talking about the global topology of the universe, the global shape. So those are more local, and they exist. I guess we think they exist. And yes, then maybe you can use a wormhole, for example, to travel from one point to another point, in an instant. Yeah, sure. But here I'm not talking about those. I'm talking about the global boundary conditions of the entire universe. So if you want to come back to yourself this way, you have to go around the universe through one of these loops. But the problem is, the speed of light is finite, and we cannot travel faster than light. At least we don't know how. I mean, laws of physics tell us we cannot. But even with the speed of light, it takes time. So I don't think, because we think the universe is not very small, of course. So I don't think this will be really practically useful. But in terms of like traveling and so on. But yeah, but what you're saying about black holes or wormholes, that's definitely the case. And if we can generate them or find a way, at the moment there are lots of theoretical subtleties and problems, basically obstacles, let's say. But yeah, so those will be useful. So the other thing about the forces that might actually give us, might have some effects that are similar to topology. So yes, sure. I mean, you can imagine that, but the point is that we haven't detected any of those things. At least within the standard physics that we work with, we know there are 4 forces in nature, and we know them well, relatively well, and we don't know of any other forces. They can exist, but we haven't seen them. So what I'm telling you about topology is not that, I'll say that, like radical. So here I'm not talking about any modification of the physics we know at the moment, and it's like, completely different thing. So it's just boundary conditions of whatever we know about the universe. So all the forces are still the same. General relativity describes gravity, and we have other forces. So that's it. But still, the question is very natural. So these are all in the universe. But what is the shape of this universe? What is the boundary conditions of these forces? But if you want to add really different force, then you have to show that that exists. And this is another thing that I've been working on for years, like detecting, like for example, fifth forces in nature. Do they exist? Can they explain, for example, the phenomenon of what we call cosmic acceleration, dark energy, for example, by just introducing a fixed force and stuff like that. But so far, we haven't had any hints of any fixed forces. So yeah, I mean, we can always theoretically assume that things exist, but we are scientists, so we have to prove that they exist. We have to find predictions and go and measure them and test them. So yeah, so for now, the answer is we haven't found anything like that. But topology, we don't know.
Oh yeah, and the only other thing I can think of is a general question. You bring up dark matter, dark energy. The 6 other dimensions of string theory. Do you think that may have anything to do with that, or if that's too out there for this?
No, actually, that's very interesting. Actually, this idea of whether extra dimensions could behave like dark matter or dark energy in our four-dimensional space has been around for many years. But recently, that's a good question that you asked now, because recently in string theory, because I really have very close contact with all the string theories in the world, the main one at least. So there is this idea these days. I don't know a lot about it, but I've been following the idea, and that's called a dark dimension. So string theorists, for some reason, for some theoretical reasons, believe, even though it's not proven, right? So it's just a hypothesis, just like a theory. So that maybe one of these dimensions, is compactified and is around nanometer size, and if it's like 1 to 10 nanometers, and this has not been, we haven't been able to detect this dimension yet, but maybe in 5 years or something, we will have technology to actually probe that. And if that exists, if this compactified dimension, which is of the size of the order of like nanometer or something, then yes, for example, that can in principle explain dark energy. That can even explain dark matter. Okay? And this is a state of the art theory within string theory community, and we will know the answer to that in a few years, I guess, if that extra dimension, compactified one exists, and whether that is the explanation for dark energy and dark matter.
Oh, fascinating! Thanks a lot.
No worries.
Yeah, thank you, Kevin. So, I think I'm not sure if you spoke about this earlier. There has been a question that was sent to me. I heard you speaking about can one hear the shape of the drum earlier? So, this question is about gravitational waves. This one came from Alan. He asked, could gravitational waves provide new insights into cosmic topology? And what are the potential signals we should look for in gravitational wave data in relation to this, if ever?
Very good question. Very good question. So, yes, well, as I told you, if the universe has a non-trivial topology, everything inside that universe will be discretized and will be correlated in a weird way. So all the modes. So this is about everything. So cosmic microwave background is about photons. We have a larger scale structure of the universe, which is basically the distribution of galaxies. That will be also like having these effects and all that. And of course, gravitational waves as well will have that effect. So if you put gravitational waves inside this universe, gravitational waves, technically, okay, let me use one technical word here at least. So we call them like spin 2 waves, because they're gravitational waves, have spin 2. And then they will also be, having these properties. They will be discretized, they will be correlated, and so on. So yes, if you detect the gravitational wave background of the universe, then we should see similar effects. But there is a problem here. The problem is that gravitational wave background, not the one coming from like um, black holes or like merging black holes that merge and stuff like that. No, I'm talking about the background one, the one coming from the Big Bang, right? So that is very, 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 very big. Okay. So far we haven't had any technology to be able to detect the gravitational waves directly, the primordial ones, the ones coming from the Big Bang, uh, directly. So we can detect them through the CMB, cosmic microwave background, because they affect the photons in there. And that's basically the polarization of the CMB. And I worked on these things. There was this whole Planck collaboration measured it to some extent, but the next instrument will be this Japanese telescope, which is called the Lightbird, and I'm involved in that as well with collaborators in Europe and the US. So yeah, for example, the aim is to measure the polarization of the CMB with a very, very good precision. And that's an indirect way of measuring the gravitational waves, and those will be affected as well by topology. And we have we are writing a paper now, should be out in a couple of weeks, and exactly showing the effect of topology on the polarization of the CMB. But the gravitational waves direct measurements, no, direct measurements I don't think will happen within the next 50 years or something. So if we ever detect those gravitational waves, then of course we can use that as well to study the topology of the universe.
Yeah, thank you, Yashar. So, of course, your group, you are one of the founders of the Compact collaboration. And earlier in one of the slides, you were talking about making circles. And I'm reminded of the work of Sebastian Chong before on protein folding, wherein he used citizen science, and then later on there was the use of AI in DeepMind in trying uh, to do the AlphaFold protein folding using AI. And then it evolved to AlphaFold 2, and now AlphaFold 3 predicts the structures and interactions of all of life's molecules. So, in relation to that, I just want to ask you a question about the work that you have now. How do you think AI, as it evolves and has been evolving very fast, especially in the past 2 years, will be able to help you in trying to give you some more information about what your questions.
Thank you so much. That's a brilliant question. Actually, that's exactly what we are doing now. Okay. So at the moment, there will be a paper. There was a paper. Sorry, there was a paper like a month ago we put out, which was the application of machine learning. Well, different types of AI, from neural nets to different types. So to study or search for the topology of the universe. That paper was the first step, though, because there are so many challenges in here. We focused only on small universes. Small means that there are circles, but we wanted to see if, for example, AI can see the circles or properties like that. And then eventually we are developing this whole machine, this whole infrastructure to look at universes that are big, larger than the size of the CMB. And that's ongoing. Within the collaboration, we have postdocs, PhD students developing machine learning, basically artificial intelligence techniques exactly for topology. And that can be used for different things. So for example, we are training the, uh, the network, let's say for example, neural network with different predictions of different topologies. So we are making millions and millions of like realizations of or simulations of the CMB and larger structure and so on for a given topology. And then we're training the network with those. And then the question is, can then the network look at the actual data and tell us whether, which one of these topologies are more likely, basically. Because there are so many correlations in here and there, and that's very hard to compute, just directly. But an AI can really help. Whether that will be successful or not, I cannot answer now. We're working on it, and hopefully in a year or two we will get to a point where we know really how well AI can help us with searching for topology. There are other ways as well. That other uses of AI in our searches as well. It's not only about classification or telling us which topology is more likely, but also in terms of parameter estimation. So I didn't really talk about that, but each of these topologies have three parameters in them. Okay, so the size of this, for example, fundamental domain. Let's say a torus. A torus has three length scales, and these are all three parameters. If you have a twist, then the location of the observer is a parameter as well, where we are sitting in this universe. So you should basically estimate that parameter. Also, the fundamental domains do not need to be having like right angles, so the angles can be tilted, and these tilt parameters and so on. So this is a huge parameter space, and the searching for the values of the parameters that fit the data, that's also hard. People do it in cosmology, like many other fields, through likelihood analyses and Bayesian statistics and so on. But again, something in cosmology is becoming very popular these years. I mean, in the last couple of years, is the so-called likelihood-free inference, where you don't really design a likelihood for people who know what the likelihood means. So you can basically directly compare the results of your simulations with data, and then search for this thing. And in order to do that, you need to you have to get some summary information from your data set. So you cannot compare, for example, millions of pixels one by one, because that's huge. That's very heavy computationally. So you basically come up with like a few numbers that have all this information, like summary information. And one thing that helps us with that is neural nets. There is this whole idea of information maximizing neural networks, or IMNNs, that we are trying to use, that exactly gives us that summary information. So yeah, lots of ways we can use AI in our searches for topology, and we're working on that.
Yeah, thank you. So Yashar, we've been here for about 1 hour and 30 minutes now. I would like to ask you how much more time do you have for us?
Right. So I can be here for another 30 minutes top. So that's the basically maximum I can say. I'm sorry for that, but in half an hour I have to go. So yeah, I'm happy to stay for another half an hour if you want.
Yeah. Yeah. Thank you so much. So, Eric, if you have other comments or anybody in the audience, if you have questions, please come up the stage. I
Why?
would like to give
Okay,
you
so
the
a quick
chance.
question. Yeah, quick question.
Oh,
So, Yashar, why are you using information maximizing neural networks? Because you just before we move on to any other questions, just if you could comment on that a little bit.
Sure, sure. So look, I mean, okay, so I don't know if you're familiar with the notion of, like, for example, Fisher information and things like that. So the point is that you have a theoretical model, okay? For example, standard cosmology, we have the so-called lambda CDM model, which is the standard model of cosmology, and it has seven free parameters. So the question is, if I want to compare a prediction of this model with the data, and data is normally like position of galaxies or like all the pixels on the CMB sky and so on. So millions of pixels or millions of pieces of information. So if I want to compare the results of simulations coming out of my model for a given set of parameters to that data set and say whether they fit or not, they match or not. So this is hard, okay? So you can show mathematically for any theoretical model with n free parameters, you only need to compare or to extract n data points from that model to compare with the data. Okay, so you don't need millions of pixels or millions of pieces of information. You just need for lambda CDM, which has 7 parameters, you only need 7 numbers. So now, how do you get these 7 numbers out of your simulations? Okay, it's because the system is very nonlinear. It's very hard to know. You start with your free parameters, like your set of parameters, and you get as output, you get 7 numbers. But what are these 7 numbers? They are like nonlinear combinations of all this information. So information maximizing neural nets, what they do, they try to maximize the information, what we call Fisher information, given this model within that simulation, right? Or also data set. So they maximize the information. They want to extract as much information as you can from that data set. It could be a simulation or it could be real data. So to get those 7 numbers, for example. So we maximize the information in a sense that maximize the information we extract. That's what we mean from the data set to come up with this summary information. So that's why we call it information maximizing neural nets. I don't know if I answered your question.
Yes. No, I was thinking like something like, like a Buckingham Pi theorem. You want to minimize the amount of variables while maximizing kind of the mapping of the space. So I'm just trying to follow up here. So
I see.
So it's like a variance. You're trying to minimize a variance, and so okay, yeah, that kind of that makes a little bit more sense.
Sorry, yes. Yeah, so that's at the level of the parameters, the parameter values. Of course, you want to find the best fit and also the variance. Like we want. Yeah, that's it. Here, I was talking about the information you want to extract from the data. So that you want to maximize. You want to get the maximum information out of it. Okay. So that's what I mean by information maximize.
Okay, cool. Thanks.
yeah. Thank you, Eric. And we have Einar who just came up on stage. I'll give the mic to you now, Einar.
Yeah, hi Cecile. Hi peoples. So I just have a short question here. If I get this right, I've been a bit in and out when it comes to listening to all what's been said here. But if the shapes of the universe might differs, it will help us to find more parallels when it comes to general and special relativity. Am I right? Or yeah, thank you.
Sorry. Okay, so maybe I try to explain this, but I'll say it again. So first of all, the special relativity is just special type of general. Well, general relativity is more general, right? That's general relativity. So that's the theory of gravity we have. which is talking about the curvature of space-time, and that's how you can get gravity, basically. So what I was trying to say is, like, if you look at general relativity, it's basically Einstein's equations. Einstein's equation is a set of equations where on the left-hand side you have something which is the geometrical property of any space you're studying, and on the right-hand side is all the energy sources. So we always say matter tells geometry, or matter tells the space how to curve, and the space tells matter how to move. Okay, so that's basically Einstein equation, but that's a set of differential equations. Depending on which space you use, something like 4 or 5, maybe 10 differential equations. Now, these are all equations that are coupled, basically. Now, these equations, like any other differential equations in mathematics, when you want to solve them, you have to impose boundary conditions. When you want to solve like wave equation, you have to say which material you are talking about and what are the boundary conditions of this material, what is the shape of this, and then you solve the equation and you get the answer. But these boundary conditions are not included in the equations. So general relativity does not have any problems with any boundary conditions in principle. Okay, so you just define your boundary conditions and just solve the equations inside this in this system. So now for the universe is the same. So we solve Einstein equations for our universe, and we get things like the universe expanding, all these things, and so on. But this is so far people have been assuming that this universe has very trivial boundary conditions, and that's how we get these things. But now they're saying why. We're asking why. We can impose other boundary conditions and solve Einstein equations. So there is no contradiction between general relativity and topology. Topology is about the global shape, and general relativity is about geometry, local geometry. So local geometry, global geometry, if you want to call it that way. So these are two different aspects of any space. And there is no problem with using GR. Of course, for other reasons, you might want to change GR or modify it, or come up with a different theory, alternative theory of gravity. That's fine, but you don't have to in order to study topology. You can still assume that everything is standard. It's just general relativity, but topology of the universe is different, and then look at the implications of that. I hope I answered your question.
Yeah, thank you. But I have a follow-up question, actually, if that's okay. So the reason why I asked is because I've heard and discussed that the issue with the EMC square is because of the expansion of our universe. So is it infinite? Is it finite? Is it expanding? Is it not? And it basically comes to that we're trying to describe the energy that we do have here. I don't know if you have any comments to that, but yeah.
Right.
But
right.
Anyway, thank you for your answer. Yeah, thank you.
No worries. So yeah, so this whole question of like expansion or contraction, or how, what's the so how long will the universe continue expanding, and then what? So these questions are about like time, like boundary condition in time, in a sense, like initial condition or final condition in a sense. So these are not about the spatial part of the universe. So topology, at least what we mean by topology here, is about the spatial portion of spatial slices of the universe. So the universe in GR has 4 dimensions, right? In a space like 3-dimensional space has 3 spatial dimensions and 1 time temporal dimension. So we are not talking about topology of time. We are not saying, oh, there is a closed loop in time. If you go in the future, you come back in the past or something. No, we don't touch time. Time is still the same. So universe can be expanding or contracting or whatever. But you're talking about that space, the spatial part of the slice of the universe. What is the shape of that? Something is expanding. Something is contracting. What is that something? What is the shape of that thing? Okay. So you can still have contraction or expansion for a finite universe. You can also have it for an infinite universe. We can have it for different universes with different shapes. They can all be contracting or expanding. So these are 2 different questions. So we are not really talking about the evolution of the universe, even though there might be some connections. Maybe for some specific topologies, the evolution, evolution will be also kind of affected in a different way. That's a different question. But for now, we are really interested in the global shape of the spatial section of the universe.
Wow. Okay. Thank you very much. Thank you.
No worries.
Yeah, thank you, Einar. So Ash is here on the room chat, and he is asking about thoughts about Neil Turok's conical topology based on the new to the tested right-handed neutrino.
Okay, well, I'm not sure which exactly theory is referring to, but well, I'm familiar with, I'm following his work. Actually, we have been planning on having discussions with him because they have some models of a universe which are not inflationary. They are not coming from this cosmic inflation. They have some other mechanism to generate the universe. And apparently, they can come up with a universe that is already homogeneous. So you don't need any cosmic inflation to make the universe homogeneous. And within their theories, in principle, you can have different topologies as well. As far as I know, they haven't looked into that yet. So this is something we want to discuss with them to see what will be the effect of that. But for now, I think they're just looking at some other effects of this. And yeah, so I don't know about exact theory model that you're talking about, but yeah, well, I'm familiar with those. So one of the things that I should say that one of the things that we will develop in the next few years is not just so far I talked about observational searches for topology, which is our main focus. And as I told you, this is basically an observational question because general relativity does not give us anything, and we need to just go and look for the topology and find it. But I should tell you that I'm very, very interested in relation connection, to fundamental physics, and I will have a postdoc joining me and GC students, and I want to really them to focus on fundamental theories like string theory and also theories like the ones that for example, theories that Neil and other people are basically proposing. So I want to really understand those because they can also help us. At the moment, we have infinite number of topologies to look for, to test, to check. But if you have more theoretical reasons for some of them to be more like motivated and so on, that would be great. So yeah, so for that reason, yeah, I'm following these things, but I'm not totally familiar with all the details of their theories.
Yeah, that's exactly the one I was referring to, and yeah, I mean, there definitely seems to be like a lot of interesting things happening in terms of like different types of topologies that are possible with different theories, and yeah, enter M string. There's a lot going on here.
Absolutely, yeah, totally. So now, in for example, string theory, there is this again another kind of new field. People are thinking about like what do they call like bubble nucleation or something. So the universe is suddenly, is generated somewhere within the higher dimensional space, and then the question is, what kind of topologies that universe can have, and does it have to be always like a spherical and like a usual bubble, or it could be more complicated. These are things that I'm talking to string theories and quantum gravity people and so on to understand better. But I don't think there is an answer to these questions at
the moment. Ash, do you have a follow-up?
No, yeah, no follow-up question, but I mean, it's absolutely fascinating area for me, and I feel like it's gonna all come together in the next a few years.
Hopefully, that's our hope as well. So yeah. I mean, the way I normally do, I mean, at least for me, I do cosmology like as a. I'm not one of those people who focus on only one thing. Cosmology, I see things kind of connected. So that's why I'm trying to, to understand what people doing different fields, and yeah, hopefully they all give us a consistent, a coherent picture of the universe at some
point. I may have a follow-up question.
Kevin, just a minute, please. I think Mustafa has a question. Anyway, I think Yashar still has a few minutes. And Yashar, I wanted to mention that I talked to Laurent Friedel also Neil Turok earlier. I hope I can invite them here with you and you may have an open discussion. It would be very interesting for all our audience to listen to. So, yeah, thank you. Anyway, I'd like to request Bob, if you can, please read the question of Mustafa here, if it's okay.
Okay, so let me see. Okay.
Sure. Okay. Mustafa's question asks, with recent advances in detecting anomalies in the CMB, what new methods or technologies do you believe could provide definitive evidence to distinguish between topological hypothesis of the universe?
Right. Okay. Good question. So one thing that we still need to understand. So we as I told you. So we think topology might be an answer to this. Maybe that's the explanation for these anomalies. Okay, but this has not been shown like in detail. So one thing we are doing at the moment is to study all these anomalies for given topologies to see if actually topology can, because there is not only one anomaly, there are many of them. And all of them are kind of showing more or less that the universe is not statistically isotropy. But whether we can get exactly those anomalies, but those features with the given topology is not known. So one of the things we are developing at the moment is exactly this infrastructure, and we want to start with different topologies and then see if any of them will explain the anomalies. Maybe not all of them, but as many as we can. So these are two fields that people are working on like in parallel, but they're kind of related. So we're also doing the same. So we are studying anomalies separately, just without even topology, just understand them better, and we might be able to even detect new ones with the future data and so on. But at the same time, we are developing all this topology work. And one thing that we're also doing is exactly the intersection, right? So how well we can explain the anomalies with topologies and so on. So this is something that I don't have an answer to, but I think the question was when we'll know this. So hopefully in the next, as I said, like 5-10 years, we are focusing on this and we're going to study this in detail as much as we can. And hopefully we'll provide an answer. But at the moment, we don't have it. There are papers on this, but we need to work more for another probably at least a couple of years to give an answer to that question.
Thank you, Yashar. So maybe two questions before we close the room. There is a question from someone, Sophia C. Can you please read that, Bob? And then we'll give the mic, the last question, the chance to ask the last question to Kevin.
Yes, indeed. Sophia asks that she's heard that Elon Musk recently said that the Earth is flattish round or roundish flat. Not quite sure exactly, she says. I would like to know what you think he was talking about with the understanding that we are just speculating.
I'm sorry, I have no idea what he meant or blah blah. So about the Earth, I mean, we know what the shape of the Earth is. There's no question about that. And I'm a cosmologist, so I mean, we don't think about the Earth. The Earth is like so tiny; it's basically nothing compared to the universe. I mean, really nothing, not even a point. So I think all these questions the Earth have been answered like for centuries. And here I'm talking about the entire universe, which has billions of billions of billions of billions of galaxies, and each one has like billions of whatever, hundreds of billions of solar systems, and like the Earth and so on. So yeah, about the Earth, I have no idea what Elon Musk meant, but the Earth, I think we know the shape of the Earth very well. So there's no question.
I agree. I can't add anything to this because I've never heard of this from him.
Okay, yeah, maybe. I don't know.
Yeah, thank you, Yashar. So, Kevin, let's give the chance to ask the last question to you.
Okay, thanks. And yeah, I tried to come up with a follow-up question. So tell me if this is relevant. Looked up, multipolar vectors and anistropy, a novel representation of CMB. Anistropy, maps involves using multipolar vectors. Each multipolar order is represented by unit vectors pointing in specific directions on the sky, along with an overall magnitude. And this representation provides evidence for statistical anistropy or non-Gaussianity in the CMB. Tell me if that's relevant.
Okay, so what I understood from the question, so if it's about multiple vectors, this is very, I don't know, whoever asked this question, I think, probably knew about these things, but that's exactly one of the next steps. So there will be a paper, hopefully soon, by the collaboration, exactly on multiple vectors, using that for topology. We are actually using multiple vectors now to combine it with our machine learning or artificial intelligence infrastructure, because we think multiple vectors can really very well basically represent the information about different topologies. And the results have been really very exciting. And so stay tuned, and there will be our results based on those as well. I agree. Those are very interesting. A lot of people worked on those in the CMB field, and but you might know that they were actually first invented by Maxwell, the famous Maxwell. But yeah, we are working with those as well.
Incredible. Thanks a lot.
No worries.
Yeah, thank you, Kevin. So we are going to wrap up because I promised Yashar that we wouldn't try to violate his deadline, which is about a few minutes from now. And I did not expect to have this many interesting questions from our audience, but I'm sure that they really love this room very much. So thank you, Yashar, for accepting our invitation and for being a great storyteller to our audience, who are also a general audience, maybe answering all kinds of questions. And I hope that we can invite you here again in Quantum Photonics.
Thank you so much for having me and for the invitation. Yeah, this was really fun. Yeah, it was great. I'm sorry that I can't stay longer, but yeah, hopefully in the future I'll be having this conversation again, and that would be great. Yeah, thank you so much to you and to everyone. Yeah.
Yeah. All right. So I'd like to ask Bob if he would like to speak before we give the mic to Darcel to help us close the room. And thank you, Kevin, Einar, Ash, Eric, a while ago, Mustafa, and everyone who came on stage. And Yashar, again, very cool presentation. So Bob, mic to you.
Thank you very much, Cecile, and thank you, Yashar. I want to say that on behalf of everybody in the audience. This is made for a very interesting Saturday, so thanks again.
Thank you so much. Thank you for organizing this whole thing. Thank you.
Yeah, so all right then, mic to you, Darcel.
Thank you, Cecile, and thank you, Doctor, for a great talk. To close the room, we're going to start our countdown from lucky number 7. Is everybody ready?
Yeah.
Ready.
7.
The 7 samurai.
7.
Ash 6.
Ash 6.
Enar 5.
5.
Kevin 4.
Red bar again, 4.
Bob 3.
3 for me, please.
Cecile Dos X.
Dos X.
Good doctor, your numero uno. Call out our last number, please.
Yeah, that's 1.
Thank you so much, Yashar, and
thank you. Thank you.
See you in the next rooms.
Thank you.
Beautiful. Thank you.